Okay. Now we have a tutorial on the communication in building that we try to give you some exercise for the topics that we described 2 weeks ago. Now the first question, it is describe the analog to digital converter, ADC. It receives an analog signal and converts it into a digital signal. The resolution of the output signal is 8 bit, okay? And the received input signal is Vt. It is a sinusoidal function, which is equal to 10 plus 10 cosine 2 pi t, okay? Now ADC, basically, it is a device to convert an analog signal, okay, into a digital signal. Okay, remember 2 weeks ago we talked about this this device. And the first question, part A, what are the processes required for ADC? Remember that we have 2 processes. The first one is sampling. Okay. And the second one is quantization. Okay. Now sampling, it is a process to take a value from the input signal at a fixed interval. Okay. For example, you may sample the input at a particular time. Okay. This is the sampled value. And the next step, it is quantization. It is a process to truncate the signal into the nearest level. Okay. And after that, you have a digital signal. Okay. Now the next one, we are going to calculate the signal to noise ratio SNR in decibel of the system. Now remember, in the lecture, we give you a formula to compute the signal to noise ratio in terms of the number of bits of the system. SNR equal to 6.02 times n plus 1.76. Okay, now n equal to 8. Therefore, when you substitute 8 into the equation, you can get the signal to noise ratio equal to around 50 dB. Okay. Now I think this is not difficult to you. You can easily apply the formula to find the signal to noise ratio. Now signal to noise ratio, it is a factor or an indicator to tell you that the ratio, the signal level between the level between the signal and the noise. Normally, if you have a higher value for the signal to noise ratio, that means the quality of your system become better. Okay. Okay, now part C, we are going to find the step size of the ADC. Now in the lecture, we give you another formula to calculate the step size. Now the step size actually, it means for the analog input, it has a range. For example, in this example, the range of the analog input is from 0 to 20 volt. This is the full scale of your analog input. And now we have 8 bits for the digital level. And normally, it gives you 2 to the power 8 or 256 level in your digital signal. Now, therefore, the step size in terms of delta V equal to the full scale voltage dividing by 2n minus 1. Okay? Because you try to divide the level for this example, you have 256.9 in a full scale range. Therefore, the number of interval you can count here, it is 256 minus 1. Okay? Therefore, by applying the formula, you have 20 over 255. And the step size, it is equal to 0.07844. Okay. Again, I think it is not that difficult because you can directly apply the formula. You can see the answer. And lastly, we are going to find the conversion at the time equal to 0.2 seconds and 0.4 seconds. I can try the first one to you. Now, at t equal to 0, you have v0 equal to 10 plus 10 cosine 10, cosine 0. Okay. Now remember the calculation inside the cosine function using the radian. Okay. Therefore, it is equal to 20. And as a result, 20 corresponding to the digital level should be 255. Okay. Or you can using the formula that 20 over I put it in here. 20 over 0.0784. And you can give the answer equal to 255. Okay. Now the other calculations, that means t equal to 0.2 seconds and t equal to 0.4 seconds. I left you to be as your exercise, and you can try to calculate the answer for the corresponding digital signals. Okay. And I will give you times after I describe the question to you. Now we move to question 2. But before we describe question 2 to you, do you have any question on question 1? Okay. Now in question 2, a system has to digitize 8 analog input signals and send out the result as a single bit stream. That means it combines 8 analog signals into a single channel. Only one ADC is available to serve these 8 channels. And assume the maximum frequency component and dynamic range of the analog signal is 20 kHz and 70 dB respectively. Now we have some questions. First, what is the resolution of the ADC? Second, what is the bit rate of the output bit stream? And you may ignore the time required to switch between the channels. That means because we have only one ADC, you needed to, the ADC will switch to different channel to serve the conversion. Now we assume or we ignore the time required for switching. Okay. Now we can see the answer. Now remember that the resolution comes from the we may using the 70B to make the calculation, and therefore what you are going to do is that you're using the signal to noise ratio formula again, 70 now using the resolution equal to again you're using this formula because it tells you that the dynamic range. You may using the same equation plus 1.676, which you set it to become 70. So after you solve the equation, you can get n equal to 11 bit. Okay. Now, any question? Now for the second part, now what is the resolution of the ADC? Now the maximum frequency of the signal, it is about 20 kilohertz. By using the Nyquist theorem, the sampling frequency should be at least 2 times of the maximum frequency. Therefore, you have 2 times 20 kilohertz, which is equal to 40 kilohertz. Now you have the sampling frequency. Therefore, if you have 8 analog channel, you are multiply each channel occupy 40 kilohertz. Therefore, the total bandwidth equal to 8 times 40 kilohertz, or equal to 320 kilohertz. Okay. And now you know that the resolution is around 11 bit. Therefore, the output bit rate it should be equal to 11 times 40K, which is equal to 440 kilobit per second. Okay. Any question? Now, in the communication system, normally we needed to have some calculations on the bit weight, bandwidth, or the resolution, and more or less you may using the equation we provide in the lecture to make the calculation. Any question? Now, if no, we move to question 3. Now, in question 3, we have a signal have the following spectrum, sampling at the frequency 9 kHz, and we are going to sketch the magnitude of the spectrum of the sampler signal. And we are also asked, is it possible to recover the original signal from the sampler signal and satisfy your answer? Now I can try to draw the first sample to you, and you can compete the others for the sampling spectrum. Now remember, now this is the original. Yes, let me see. Okay, someone asked me 11-bit. Now 11-bit come from here. Okay, that means the answer of first part. Okay. Okay. Now now for question 3, now we have 3 samples. 2 kHz, 4 kHz, 6 kHz. Now remember in the lecture we tell you that when we try to take the sampling of the frequency spectrum, now we will make our zero axis become a mirror, and we copy the now we copy the frequency sample along the mirror. Therefore, at the position of -2 kHz, you copy this sample. Okay. Now the others you can try. And after you make the copies, now the whole spectrum you will move to the position at the sampling frequency. Now the sampling frequency is 9 kHz. Therefore, 9 kHz is one at for example here. Okay. And now you are trying to make a mirror image so that you move the y-axis into here. And you copy the frequency spectrum along the 9 kHz axis. So at the position of 7 kHz, you have this one. At the position of 11 kHz, you have a component. You copy this one. Now, the calculation is very simple. You add 2 to 9, you have 11 kHz. You add -2 to 9, you have 7 kHz. Okay? Now, therefore, you try to compete the other component and draw the sampling spectrum. Okay? At the end, you may ask, tell me the answer whether the sample signal can be recovered so that you can extract the original data. Okay? You can see something happens after you draw the picture. At that time, you can determine whether the signal can be restored completely. Okay. Now again, I let this question to become your exercise, and you can try this question. And after we describe finish the question 4 and question 5 with you. Now, any question on question 3? Now we move to question 4. Now in question 4, we have a voicemail system supporting 50 users is to be deployed, and it has a resolution of 8 bits and sampling rate of 8 kHz for storing the data, and estimate the amount of storage requirement if each user is allowed to have 10 minutes for voice recording. Okay. Now, in this question, we have a voice recording to be done at a minimum of 8 kHz with a resolution of 8 bits. So that for each user, 10 minutes storage will require okay, let me see. Okay, now you require 8,000. Now this is the 8 kHz multiply the number of time, okay, the amount of time required to storage, and you require 10 minutes. Each second is each minute has 60 seconds, and because the resolution is 8 bits, 8 bits corresponding to 1 byte. Therefore, you do not need to multiply by 1 byte, or you just simply write down multiply by 1 byte. And after you make the calculation, it gives you 4.8 megabytes for each user, right? Therefore, for 50 users, it gives you the total amount of storage equal to 50 times 4.8 mega, which is equal to 240 megabytes. Okay. Now this example tells you that without compression, you will spend a lot of storage capacity to save your data. Therefore, we require to have compression in order to save our storage space. Okay. Now, any question? Now, if no, we move to question 5, and we are going to calculate the minimum bandwidth requirement in bit per second for an internet-based audio application with the following information. It is 8,000 samples required to transmit in 1 second. The resolution of sample is 4 bits, and the Ethernet is used with a payload of 174 bytes per packet, and the overhead of the Ethernet packet is 26 bytes. Okay. Now we give you the solution. Now 4 bits per sample and 8 4,000 samples per second, it means that in 1 second, we have 4,000 bytes of the data in a transmission. Okay. And now for each of the packets, each packet, the payload means the data. Okay. The data size. The data size is 176. Together with the overhead, you have the size of the packet. The size of the packet equal to 174 plus 26, and it is equal to 200. Therefore, the number of packets you found now the number of packets you have (4,000 over 200), or actually you should use 4,000 over 174. Okay. And it is R1, you should use 23 packets to transmit right? Because you should divide the 4,000 bytes and fit into the Ethernet packet. Okay, and when you make the calculation, 4,000 over 174, it should be equal to 22.7. But you needed to send all the data, therefore you should use 23 packets. And now the number of bits required equal to 20, or the bit weight. It should be equal to 23 packets times 200 times 8. Because you have 23 packets, and each packet occupies 200 bytes. Each 1 byte equal to 8 bits. Therefore, it gives you 36800 bit per second. Okay. Any question? Now you can see that the question relating to the communication system is not that difficult, right? At least it is simpler than the questions in the vertical transporting system, right? Uh, and now I hope that you can understand what we told you this today. And for the remaining time, you can try to complete the question 1 and question 3. And at the end of the lesson, I will show you the answer. Okay? And if you have any question, you can raise your question to me. And now please try the question 1 and question 3. Okay, I think most of you can complete the question 1 and also the question 3. Now let me show you the answer. Okay, now for question 1D, you have the conversion for 0.2 second and 0.4 seconds. And when you substitute 0.2 and 0.4 into the function, you have V 0.2. It is equal to 13.09 volt. Therefore, after you make the conversion so that you have 13.09, you divide it by the step size 0.0784, and you can have, after rounding, you have the level become 167. Okay. Now similarly, if you substitute 0.4 into the function, you get the voltage value equal to 1.91. And again, you're using the same method. Okay, divide it by 0.0789. And after rounding, you get the level equal to 24. Okay, and do you get these two answers? Any question? And now that we come to question 3. Now, I asked you to complete the other frequency signal. So, for the original spectrum, at the position minus 4K, now you have this signal. At minus 6K, you have this signal. Okay, so you will repeat 4K, 6K, minus 4K, and minus 6K at the positions at the center of 9 kHz. Therefore, at 13K, at 15K, you have this spectrum. At 5K, you have this one. And at 3K, you have this one. Okay. And now you can see that the original frequency spectrum has been corrupted because the maximum frequency is up to 6K. If you make a low-pass filter that can cover just above 6K, you can see we have additional frequency component inside, and therefore we can say the frequency spectrum is corrupted and it cannot recover the original spectrum. And this effect we are so-called the aliasing. Okay? And do you get the same picture? And do you have any questions? Okay, Now, if no, that's all for today's lesson, and I will adjourn the lesson. If you still have any question, please post your question to me. Thank you. Bye bye.